Okay, so what I want to do is just quickly work through the bar hanging in its own weight example, so that we can just highlight one or two things. I just want to show you what happens if we stuff up this consistent node loading. If we have just put in our own values or our own split 1/3, 1/3, 1/3, or a quarter, half a quarter, if you don't do it properly on a method, I just want to show you what the implications are. So this is why you need to really understand that when you compute distributed loads and stuff in finite elements, we will use consistent node loads, and we will do it properly. I'll at some point talk about Sympy+Numpy's principle and the modeling implications that has. Okay, but for now, everything you do when you see distributed load, you compute it this way. You don't guess what the split is. And I'll show you why that implication is quite important. Okay, so bottom line is we follow the same principles as before. This time around, what I'm doing is I'm combining now NumPy and Sympy. So for those of you that would like to leverage the Sympy knowledge, and the reason for this is just there's a drive lately in some of the packages. So maybe what I'll do is I'll just quickly open up here, and I just want to show you Phoenix is one of the open source projects. So there are definitely some finite element software lately that are making use of symbolic and numerical computation. So Phoenix project is one example. So Phoenix is a computing platform for solving PDEs, and this is an example of type of an let's say a related to the weak form that you would like to solve, okay, variational problem, which is related to the weighted residual approach that we have. But the bottom line is if you look at this, and you can see sort of this V is sort of related maybe to yeah, it depends on what let me not confuse the issue. Let me not talk about what exactly what the physics is, but I just want to show you how close this maps to what you see here. So if you say essentially here there are some trial functions U and P, so U and P, and look at how they write down the system here at the top as a sorry, let me just quickly how they write the system here at the top in terms of how it would look inside sort of a Python environment. Okay, so this is important to understand that they are making use large extent of symbolic computations and a mixture of symbolic numerical computations. So, and this advantage of this, it allows you to get sensitivities out, etc., etc. This is, to give you an idea, Phoenix project is a completely open source free program. Okay, so you can download it, you can use it, it doesn't cost you a cent. You can set up your own equations that you want to solve even. So I really encourage those of you that have appetite and energy, please go and have a look. But the bottom line is, let me just go back to the binding its own weight. Here's just an example of now combining symbolic and NumPy. But in general, we'll leverage the NumPy. But I'm completely open. If you are lazy to differentiate, please go in and just define the shape functions symbolically and then differentiate them and work with that. You're more than welcome to do that, and I do encourage that as well. Okay, but I just want to make sure I protect students that might get confused when they start combining Sympy and NumPy. If you get errors, just check the type. So that's my suggestion. So here's essentially just the bar hanging its own weight. The bar's got again a length of 1. Here is essentially the shape function, the isoparametric formulation that we set up, all in symbolic form now, because psi is a symbolic variable, n1 to n3 symbolic, and then we just go through this derivation, derive by array x with respect to psi, get the psi dx, set up the B matrix, which is this derived by array n comma psi. What's nice is here just you explicitly see now you're differentiating x with respect to psi, etc. And you get the formats of B out, you get BMAT, which is essentially the matrix transpose to make sure it's sort of a row. And now it's B transpose B, B transpose EB. So that's essentially what we get, the B matrix out, integrate the stiffness matrix. Integrand of the stiffness matrix is just this B transpose EB A dx d psi. And now we can just go and integrate this by subs, the right values in there. Okay, so this is just again to show you that the nice thing with following this approach is you can very quickly change your shape functions, come up with your own shape functions. Just remember that the sum of them needs to be equal to 1, otherwise you can't get rigid body motion without having crazy stresses in there. Okay, so then the traction is, again, we have this n matrix, times dx. So this is the integrand for that. Evaluate the integrand using two-point cast rule. And all that you have to keep track of is what is the highest order polynomial in here, what's the highest order polynomial in here, and then you can figure out what is the appropriate cast rule to get that thing to integrate exactly. Okay, we'll extend our understanding of integration next week, because we're going to talk about full integration and reduced integration and what the meaning of full integration is. Because what I'll show you next week is when we have mesh distortion, then these integrands are not exact. They are not exact. And why are they not exact? Well, we know that this is exact when it's polynomials. So the implication is that maybe these things are not then polynomials. They become rational functions when we have a distorted mesh. And I'll show you that next week. But bottom line is, the solution of the reduced stiffness matrix we can now solve with essentially with the right hand side. Okay, and here just moving that part across that stiffness matrix to the other side. So just as a reminder, although I multiplied by 0, it has to move to the other side in case it is not a zero prescribed displacement. Okay, so and then we can set up the whole solution again. After that, we can get the displacement field, and this is now again in terms of psi. So we're going to use Sympy, symbolic. So n is, remember, is symbolic, symbolic variables. Strain bmat dot q, stress, internal force. And when we do that, we can see this is sort of what we get out. And here I can ask ourselves, does it make sense? So at x equals to 0, which is sorry, at psi minus 1, we get no displacement. That's exactly satisfied. We see this displacement loading varying like this, and so you can ask yourself, do you agree with this? Remember that the loading is at the top is a whole bar's hanging, and at the bottom there's no weight hanging from that material at the bottom. So we kind of see sort of what we expect to see, that this sort of a nice, quite quadratic kind of relationship that we get out. Okay, so when we look essentially at a uniform bar hanging its own weight, that load is decreasing linearly as we go from top to bottom. So what we see is essentially the strain. You would expect to see the highest strain at the top where the whole bar's hanging, and at the bottom you would expect to see zero strain because there's no tractions, nothing applied at the bottom of that bar. So that's essentially, we see down that strain there are zeros because we also expect zero stresses there at the bottom. Okay, if this wasn't the case, then we might end up computing a non-zero traction at the bottom, okay, which is not great. Well, not because that's means that we're not satisfying our applied tractions. Okay, and then essentially this is just the internal force. So everything looks as expected, and you can go and compare this now to that hand calculation that we did, that approximation where we had the whole 3D approximation. Please go and make use of this opportunity to go and compare the solution against that. Okay, the next thing I want to talk about is if we were to talk about splitting the body force. Okay, equally over 3 nodes. I just want to show you what happens here. Okay, maybe before I do that, I just want to, these things you can go and compute yourself. So read carefully through here. I'm not going to go into detail and read it just for you, but this is just part of the critical interpretation of the results. Okay, so that we make sure that we understand that the solution is what we expected. Okay, I'm just going to show you what happens now. What happens now if I stuff up my distribution of my load across these vectors. So I'm going to make it a 1/3, 1/3, 1/3 and show you what happens. So this is just the same solution, just 1/3, 1/3. Everything looks above board, zero for displacement there. It looks, but look at that. I would expect to see something that maybe tapers, that goes down to sort of a nice slope there at the bottom. Yeah, because I don't want to see any. I want this thing's derivative to be 0. Because otherwise I have stresses here. So there's definitely going to be a stress there at the bottom, which is not, there's already a alarm going off. What is going on? Look at this strain field. Look at this. The strain field here at the bottom is 1. Look at the stress. The stress there is 20,000 at the MPa. It's only 55 at the top. But look at the difference between the maximum now. Look at my maximum stress that I had here. Okay, so here I had maximum stress of up to 80,000. Okay, just bear in mind what is going on here. 80,000. Look at my maximum stress now. 50. All of a sudden I'm under predicting my maximum stress. Yeah, in tensile stress. So this is this stuff up is a disaster, because it means I'm completely under predicting my stresses, which is not great. Look at this at the bottom, there's still stresses there. Look at this essentially internal force. The internal force at the top is just about 550, at the bottom it's 20. I'm supposed to see something around about 765. That's the total load at the top. 765, and I look here, I can see that's about 765. So if I just stuffing up this split 1/3, 1/3, 1/3 as opposed to 1/6, 1/6, 2/3, I'm making a disaster. Let's just for the fun make this also something like maybe a quarter and a half. Again, you can go and play with this. Please go and have fun. So I'm making it a quarter and a half. Okay. So half is now in the middle, the mid side node. And if I do that, look at this kind of stuff again. You can still see that is not sloping down to 0, so that I expect a 0 strain and a 0 stress there. Look at this. Look at this. Look again there. It's slightly better, higher at least, but it's not at 80,000. This is not at the 780 or 760, whatever that I expect to see. Still, look at that. At the bottom, there's a traction at the bottom all of a sudden. This is insane. So this thing is not working at all. Even if I do a split, sort of a quarter, half. So please take note, consistent node loads is critical in finite elements. Don't stuff it up, please, because you might end up really making poor approximations because the loadings might not be reflective of what you would have liked. Okay, so take note of that. And this is sort of the notebook of this. Please work through it, and please go and compare against the 3-dimensional hand calculation ones, and convince yourself of whether you're happy with the solution and that you're in agreement that this is a good approximation. All right.